Hi, this is Mark Weitzman. I want to do another problem from Goldstein. Last time I left off that it's chapter 6, special relativity, at least in the first edition. I think it might be chapter 7 in the second edition because they rearranged the chapters. But anyway, this is problem 12 in the first edition, 25 in the third edition of Goldstein. It's also problem 4 in chapter 12 of Jackson's book on classical electrodynamics, the second edition. And I'll just quickly read the problem. This is a very basic problem, but it has a very interesting aspect to it that I wanted. That's why I put this problem up. A particle of rest mass m, charge q, and initial velocity v0 enters a uniform electric field E perpendicular to v0. Find the subsequent trajectory of the particle and show that it reduces to a parabola as the limit c becomes infinity. So the setup here is very simple. So here's the y-axis, x-axis. We have a particle of charge q and mass m. It's initially moving at velocity v0 in the x direction. There's an electric field everywhere perpendicular to that initial velocity of magnitude e. So I'm not going to do anything fancy here. There's no reason to do any co-moving frame stuff here. This is all very basic. I'm just going to write down, start with the relativistic equations of motion, the derivative of the momentum, 3 momentum. Like I said, I'm not even using 4 vectors. Derivative of the momentum with respect to time is equal to the charge times the electric field. This is the Lorentz force. There's no magnetic field. Newton's law, change the momentum with respect to time, but this is now the relativistic 3 momentum. So if we write this out in components, we're going to get our first equation. I'll write it down. 1 d dt m vx. Vx is the component of velocity in the x direction over the square root of 1 minus v squared over c squared. This whole thing is equal to 0 because there's no force in the x direction. E is perpendicular. E is a component in the y direction. And so this equation implies that the x component of momentum is constant. So we're led to a very simple equation. Vx is equal to v0 over the square root of 1 minus v squared over c squared divided by the square root 1 minus v0 squared over c squared. Because in the initial conditions at time t equals 0, v is just v0. So this factor becomes 1 and we get vx equal v0. This is not a solution to our problem because it has v here, and v itself, v squared, is equal to vx squared plus vy squared. So this is an implicit relationship, but eventually we're going to have to do better. And now our second equation, I'm just going to write the force equation in the y direction. It's the same thing basically. d dt mvy over the square root 1 minus v squared over c squared equals qe, because we have an electric field in the y direction. So this equation implies that Vy is equal to Q E T over M times the square root 1 minus V squared over C squared. Again, we can check it out at time t equals 0. This is 0, which is correct for the y component. And again, it's implicit because this includes Vx squared and Vy squared. So now, what you do is you square those two equations. So you get like Vx squared plus Vy squared is equal to QET over M 1 minus V squared over C squared plus V0 squared 1 minus V squared over C squared divided by 1 minus V0 squared over C squared. And this is V squared. So you can see we have V squared here. The only unknown variables here are V squared. We can solve for V squared. And manipulating this algebraically, you can get the following, which is what we really need. 1 minus V squared over C squared equals 1 over QET over M squared plus 1 over 1 minus V0 squared over C squared. Okay. So this is, I'll put label 3 here, box it. So now we have this factor here, and we can substitute it in these equations, and we can get first order equations for Vx and Vy. So when you do those substitutions, you get Vx, which is defined as dx dt, is equal to V0 over the square root 1 plus alpha squared t squared. And I'm going to define very simple. Alpha is like the basic constant in this problem. QE over MC times the square root 1 minus V0 squared over C squared. So this over here is a very simple differential equation. You're just integrating it directly. And again, you can use software, look online, make a trigonometric substitutions, very elementary calculus. This time you'll do a hyperbolic substitution instead of a trigonometric. And so you can solve for x. You're going to get x is V0 over alpha, inverse hyperbolic sine of alpha t. And again, to check that, we're using our initial conditions. Let me write the initial conditions here. T equals 0, x equals 0, y equals 0, Vx equals V0, Vy equals 0. Okay, so the particle actually starts over there. I drew it there, but it starts over there. This way I don't have to keep track of any other constants. So t equals 0, x equals 0, good. And now do Vy. Vy, which is again is defined as dy dt. This is an even easier differential equation because you're going to get QE over M square root 1 minus V0 squared over C squared. So this is just alpha C actually, times T over the square root 1 plus alpha squared T squared. Like I said, this is even easier to integrate because you got the T squared in the denominator and a nice T in the numerator. So this leads to y equals c times the square root 1 plus alpha t squared minus 1 over alpha. And this is the solution to our problem. And I'll take the c equal to infinity limit, and I'll discuss why I thought this was an interesting problem. I mean, the problem itself is not that interesting, but the solution and what it says about relativity is interesting. Okay, first of all, just commenting on the y motion. This is what's called hyperbolic motion under a constant force. And if you would actually write this down, you would get this equation. It's called hyperbolic motion because it has the equation for a hyperbola. In the yt plane. So this is the type of equation you usually get when you have hyperbolic motion, a force, constant direction in the yt plane. The x motion, on the other hand, is logarithmic. If you take like the limit as t goes to infinity, so the cinch becomes easy to evaluate. So as t goes to infinity, you'll find that x is equal to v0 over alpha ln 2 alpha t. So as t goes to infinity, x goes to this value. And so x goes to infinity, the particle does go off to infinity even as it goes like way higher in the y direction. What's interesting is if you take the derivative of this, the asymptotic value of Vx goes to 0. Now, there's two things that are surprising about this. The first is, you kind of say, well, there's no force in the x direction and it starts out with velocity v0. Why doesn't it keep its velocity? Why does the velocity go to 0? And the answer is because in relativity, the trajectory, let's just draw the trajectory. Eventually, under a constant force, the velocity is going to approach the velocity of light. The y velocity is going to go, let me see if I have an equation for Vy. As t goes to infinity, this becomes alpha t. The t cancels, I'm going to get alpha, and this is alpha c. So it ends up being c. So the y velocity is always going to approach c asymptotically, which doesn't leave any velocity for the x component because I erased that equation, but vx squared plus vy squared equals c squared. So that's what's interesting about this problem. Of course, you could also see it, the momentum is conserved, and the momentum is m vx over the square root of 1 minus v squared over c squared. And the only way, since this is the gamma factor goes to infinity, so the Vx factor has to go to 0 in order for this to be a constant. So this is what's interesting about this problem, is that even though there's no force in the x direction, the x velocity does slow down and go to 0. Let's get the parabolic limit. Let me just erase this. C goes to infinity. So when C goes to infinity, alpha C goes to QE over m times the square root just QE over M actually, because C goes to infinity, and that will kill that. That will make that 1. So that's what alpha C goes to. And so X is equal to, now under this, we have V0 over 2. Since alpha goes to 0 basically as C goes to infinity, this becomes small, and sinh of a small number is the same as the number. So this thing becomes just V0, that's not 2, that's alpha, sorry. V0 over alpha, alpha t, is equal to V0 t, which is what we expect classically. It's just moving along with speed V0 times t. And y is equal to C over alpha. Now alpha t again becomes small, so let's expand this square root. Get 1 plus 1/2 alpha t squared plus dot 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 minus 1, which is equal to, we have an alpha squared, so we get alpha c t squared over 2, which is equal to alpha c goes to QE over M, which is equal to 1/2 QE over M t squared, which is again exactly what we expect. Y equal 1/2, this is the acceleration, QE is the force, divided by M, y equal 1/2 AT squared. And this is of course a parabola in the XY plane. Y is going to equal to 1/2 QE over M x squared over V0 squared. So this is a parabola. Okay, so as I said, there was nothing difficult about this problem or anything, but it does show you that in relativity sometimes you have to be careful, because the force equations are coupled, unlike Newtonian mechanics where the x, y, and z directions are uncoupled. So this gamma factor makes all the difference in relativity, because gamma is equal to 1 over the square root 1 minus v squared over c squared. So if we take the x component of this equation, we'll have fx we'll have something that looks like this, 1 over the square root of 1 minus, I'll write this as dx dt squared plus dy dt squared over c squared times vx. So this is the difference between special relativity and Newtonian mechanics, is that the force couples not just to the x component velocity and derivative and everything, but it also has the y component of velocities. And that's what makes, sometimes you'll get some interesting effects. So thank you very much for watching, and I have another problem coming up on special relativistic perihelion precession. It's a little bit more involved, but it's interesting that most of us think of general relativity precession, but even special relativity has precession. Of course, anything that's not strict Coulomb law will have a precession, So if it's not exactly 1 over r squared, and special relativity gives corrections essentially to that, then you're going to get precession. I'll see you next time. Thank you very much.